All right. Well, first I'd like to thank Serge and the other organizers for inviting me. It's nice to be here. I'm going to tell you about using emulators for forecasting natural hazards and doing uncertainty quantification. So here's a recent, I'm going to talk about the volcanic hazards, although I think our approach, although there are many things that are specific to any kind of real problem, is quite general for natural hazards. So you can see volcanologists fall here on this scale of who you should be worried about seeing in the news. And of course, it's in the news quite a lot, right? And there's a lot of money and human cost that comes from these kinds of hazards. So here is I'm not going to try to pronounce it, but the volcano in Iceland is estimated 2 to 5 billion, especially loss in air travel in the UK. There's other nasty volcanic hazards. This is Lahars in Colombia in 1985. Here there's debris from a volcano that gets remobilized because of rain or because of melt from snow. And you have this sort of nasty mudslide, honestly quite similar to the mudslides that were in California recently, where you sort of have this sludge, and it's a two-phase flow between water and various sizes of particles. And these sorts of granular flow problems have this nasty property of pushing the boulders to the front. So you get this sort of train of debris headed at you. And there were many fatalities from this. So the whole field of volcanic hazards started over a century ago now, looking in Martinique. And this is just really the issue that I think it's kind of human nature, but certainly is how geologists tend to think, is that the volcano is going to behave like it behaved last time. So the last time for this eruption was about 50 years prior, and it had puffed a little smoke and went back quiet for a while. And then this was ended up being a massive pyroclastic flow, which I'll focus on today, that killed 30,000 people. So these are sort of massive granular flows that you can't outrun. Okay, so here's a recent bit in Nature Correspondence, I guess from October, and I just want to focus on this risk assessments face legal scrutiny bit. And I'm going to zoom in on the part that I think is quite relevant. So as claimants test the timeline of circumstances leading up to such disasters, scientific records and legal duties of care will be subject to intense scrutiny from peers, lawyers, and the media. Earth scientists must confront these pressures with rigorous data monitoring, analysis, and interpretations, combined with accurate public communication of any scientific uncertainties. So, I mean, obviously, you probably the Italians who were jailed popped to mind, but I really think they were referring to some lawsuits in Japan where people were hiking near a volcano and from some ballistics were injured or killed. And they went on to sue the equivalent of the Geological Survey and the prefecture for not warning them properly of the hazards. Okay, so this is a project that's been going on for a decade more or less, and I think any sort of project like this really takes different kinds of expertise. So this is sort of our core group with the Bonnie who wasn't there that night. And there's been a lot of really good graduate students and postdocs involved in this as well, right? And so I'm a bit of a hybrid person, and some of you recognize the statisticians in the back, applied mathematician, HPC, and this woman next to me in the front is a geologist, and quite literally keeps our work grounded, right? Pun intended. So it keeps it relevant to her community, which I think is why we're doing this. Okay, so I want to again focus on pyroclastic flow. So we can see the nose of the flow there, and it's a dense granular flow. Let me get out of this for a second. So I was really impressed with that PDF movie the other day because I managed to embed this movie in my PDF, and I can run it, and then it kills my talk. Okay, so here's a pyroclastic flow in Japan. You can see a sort of rapid granular flow. It's going, many kilometers per hour. It's not something you're going to outrun, and it's going to basically destroy anything in its path. There's other sorts of hazards that plume of smoke is quite nasty above it as well. That's not part of our modeling. These people are quite unlucky, right? So this is a sort of thing that we're thinking about, these flows, right? So massive, hot, granular flow from the volcano, right? So this isn't Italy. This is closer to Mount Pinatubo or Mount St. Helens. I think you get the idea there. Okay, and there's volcanoes all over that are, sort of on at the moment. There's one you might have heard of this fall called Mount Agung in Bali. Right, so this is what the hazard map for Mount Agung looks like, and this happens to correspond with a deposit map from their last eruption, which was, I think, in the 50s or so. And I know that this isn't a very good quality picture, but in red we see the extent of the pyroclastic flows. In purple we see another associated hazard called a pyroclastic surge. The yellow there are deposits from lahars, those sort of nasty remobilized flows. And then you can see these circles, and those circles are what the evacuations are based on, right? So it's very distressing to know what the next event there will look like. I mean, did it happen to go in the same direction? Did it, what was the scale? What would happen if there was a bigger event? But then everything is based, basically on memory. So Montserrat's sort of by far the best record of volcanic data ever. And let me show you what this data looks like. So here I have sort of a faux volume on a log scale radially, and then I have valleys that we know that the flows went down. So I have the arcs that represent the valleys and some jitter just to give you a sense of a number of events. So, it's really not far from uniform on a circle. And then we have a log plot of number of events. Here's annualized and the volume of events. There's some censoring that goes on for the small events, but this really isn't that far from linear, right? So I want to think about short-term forecasting, which really, not that there of course are more uncertainties, but really goes into the sort of scenario modeling. Right. So what is how big is the next event? Right. What's the probability of that? What valley does it go down? When is it going to happen? Right. And then of course we have epistemic uncertainties. Right. And here I think about splitting these into this means sort of imperfect descriptions. Right. So my probabilistic models aren't perfect, often because I have limited data. This could be physical parameters in the physical model we're looking at, or parameters in the physical model. Certainly, we're interested in numerical resolution and digital elevation maps, which introduce a lot of uncertainty. It's beyond the work I'm going to talk about today, though. But certainly open, especially, I would say, the uncertainty in digital elevation maps is a really big open problem. Okay, so here's a linear fit to this log plot of data at Montserrat, and we can sample that Pareto distribution we're assuming there, and we can see that more than half of these negative slopes in the Pareto alpha are less than 1. But here's what you can imagine this would look like then if I plot a handful of these samples, right? So this is sort of what the data is telling us is reasonable. But it also tells us that there's a really good chance we're in this heavy-tailed case. Right, so I want to talk a little bit about rare events. So Pareto model, is much more likely to observe future volumes that exceed those in recent history. And I just want to compare a Pareto to an exponential here. So I have 10 volumes in my record, so 1 through 10. And if I'm in the sort of exponential case, the probability that my next volume would be 10 times bigger than any of those previous volumes is about 1 in 200,000. So probably wouldn't be too worried about that. But in this sort of heavy-tailed Pareto case, being 10 times bigger than my previous volume is 1 in 100. Right? And these are the sorts of probabilities that we should be quite concerned about, that we would be dangerous to ignore. Okay, so there's lots of modeling that can be done sort of for long term, but I want to focus on short term, right? This is what we're interested in. And we can see that we have this non-stationary behavior. So I have sort of a more active period, and then it tapers off some, more activity tapers off, and we're sort of cycling back and forth. So when I think about modeling, this is sort of a Poisson process that switches rates, right, at random times. And then I have this interesting sort of feature with the volume. So here I've broken down time, so time goes across. I've broken this down by ending epochs with events that are bigger than 6 million cubic meters, and then which are in red, and then any black events are the smaller events until the next big one. And you can see that there seems to be some preference there, that the small events lead to a big event that's going to end that epoch, and then there's a bit of a random walk, right? So these are the assumptions we're making by looking at this data. Right, so here's our model we're proposing. So we're going to cycle between sort of low activity periods and high activity periods at random times. We're going to learn from the data we have and then forecast forward. And this is a sort of result we would get, right? This sort of two-level type Poisson process. And then we want to model these rates. So we're going to assume that these are gamma distributed. And here we have a prior density, which is basically gamma, except we have this sort of repulsion term to keep these rates from collapsing into one rate, right? So if that R is bigger than 1. And this is what we get out of our MCMC scheme looking at that kind of model. So you can see some uncertainty in the transition, but certainly more uncertainty in the rates, right? So it went high and then low and then high and then low. And if we plot this, this model against our data effectively, right? So when I'm in the sort of gray-blue here, the model says it's in a high rate. The transition, there are these sort of dark blue lines. There's more uncertainty in my transition where those are fatter, right? But this is the sort of thing we're seeing, but it captures this behavior quite well. And then for the random walk, I want to think about using a von Mises distribution. Right, so it's basically a Gaussian circle that's centered somewhere and has a sort of a variance term, sort of a thickness to it. And this is if kappa is 1, that dark line, just for reference. Larger kappa is going to get you tighter. Okay, and here's what we're going to do. So I have this von Mises distribution centered in this valley, or centered in a valley. And then when I hit a 6 million cubic meter flow, I'm going to let that take a random walk. That random walk is also von Mises. And we can write down the posterior, looking at this Pareto density that we're already assuming for the volume, and the sort of random walk on the angles. And here are samples from this guy. So here are samples from the means in each of these epochs. Then I can look at actually sort of a retrospective probabilities based on this model. And we can see so the valleys it went down is where it's colored dark blue. And we can see for most of these cases, the model did a good job at predicting the valley that it was going to go down based on the data it had to that point. It's not perfect, but it certainly is reasonable model. Okay, and again, we had these posterior samples for alpha. And so here's a game we're going to play. So use data from 10 years of data or so, and then forecast forward for a couple years. And here's our trace plot. So now I have time going up. So this is where things are very well constrained from the data. This is sort of the figures I was showing you a bit ago turned on their side. Right, so this was an on period here and here, and then an off period in between. And then this is where I no longer have data. So now these colors are cycling on and off. This is a very slow mixing process because it's so constrained here to get this to really explore the space when in forecast mode. But now we can sample from this. So I have samples from this model. So I'm looking at the cumulative volume in our forecast range. And I did this sort of forecast where I knew what the data was going to be ahead of time, right, to compare to, right, because we had data from 2006 to 2008. And our data looks like one of our samples, right, which is encouraging. Here's what our samples for, and sorry those dots are probably quite small. The purple ones maybe you can see a bit better. But time is radial here, and the von Mises is not too tight, so I'm sampling around the circle, but I'm focused more along this purple line. And then this is my big event, in this sample, bigger than 6 million cubic meters. And then my center takes a random walk to this green line. Then things are centered around my samples are centered along the green line until the big event, and which was this green dot here. And then forecasting forward, I'm centered along the cyan line. Right, so this is how our samples are going. And right, and so here we have sort of all the samples together. So we have our frequencies of events at the top. And we can see actually samples from that make sense, right? We have lower frequency, then it ramps up for a bit, and then it tapers off again. Here we have the angles, so the central angles in blue. And we can see that the angles are still kind of spread out, but they're more focused. We have more of them where the intensity was higher. And then we switch central angle, and the focus switches. And again, here is this sort of cumulative volume plot for this one sample. Right? So this is what a sample looks like. And here we're conditioning on the valley I'm starting on. And this is really where sort of precursor information or monitoring information could be useful, because we know usually where the dome is growing. So if the dome is growing toward the east or toward the northwest is what I was considering initially. And then I'm looking at the probability here of the next event being greater than 10 million cubic meters and going in this northwest valley that I'm interested in. Right, so we can get these probabilities, and that's great, but if I haven't had a 10 million cubic meter event go down that valley, I don't know what damage it's going to do. Right, so this is really what we want. And the rest of this talk is to how do we get to this point. Right, so now I'm forecasting 90 days and 180 days into the future, where I've centered going toward this valley that we're looking at, or where I've centered going to the east. Right, and we can see how these probabilities are changing, and I think in this sort of construction of the probabilistic hazard map, there's not one map of interest. It's how these maps change under different models. That's what we're interested in, and when we can update them with precursor information. Right, though, so we don't have data beyond this, right? So we have models, right? So we rely on physical models. Here we have a flowing mass. So we have the height of the flowing mass normal to the hillside, which is in Z. And basically this says that we can't flow through the ground or through the top, but we might pick up pieces of the ground as the flow goes. If we look at sort of a depth average version of this, we end up with a hyperbolic PDE. I just added that since we've been talking about so many elliptic PDEs. But basically, we have continuity of mass and momentum. And here, these are gravity-driven flows. So we have gravity pulling us down on the momentum term. So that's encouraging the flow. And what we're being slowed down by is friction. So we have friction between the grains and themselves, which is the sort of red term. And we have the friction of the flowing mass over the ground. Right? So this is This is the model we're considering. This is just to say that someone thought about how to do the computations carefully, and those computations take an hour, maybe 20 minutes these days, but they're not cheap, right? And each of them needs to be initialized with some volume and direction. So here's what 4 of these runs look like, and I apologize, the color scales are different, but you get the idea. So we're looking at the maximum height at any point that's colored. And you can see we have this really sort of complicated spatial footprints of these flows. And we could also think about these being 4 samples from some scenario distribution, like maybe the one that I was modeling earlier. Right, so we're going to do Monte Carlo, and here's my Monte Carlo cartoon. So I have my physical scenarios, and I'm thinking about scenarios that lead to catastrophe. And so here, out of my scenarios I ran, 4 out of 30 led to catastrophe. And then pick on Serge. And then Serge says, your modeling skills are quite weak. You really should be using this model instead. And now if you're doing a very naive Monte Carlo, you'd be rerunning these things and say, well, under this model, now I have 7 out of 30 samples for my probability of a hazard. So that's unfortunate, right? So we know Monte Carlo's slow. It's inefficient because there's lots of small volume events, right? So that's an issue. But the sort of inflexibility that I was getting at, it's non-trivial to explore different scenario models, right? That's sort of the aleatoric front of the UQ. And you could think these last 2, you might think that these last 2 could be solved by importance sampling, and I don't think they can in this problem. So I want to tell you, sort of, just to illustrate what I think the issue is. So say you flip a coin 100 times and you want to know the probability of, right, so you step to the right if you get a heads, and you step to the left if you get a tails. And what's the probability that you finish 70 steps to the right or more? It's binomial. You can write this down. But if we simulate it, well, of course, if you simulate this and you let it run for the rest of your life, you're never going to see it, right? You're never going to see 70 heads. If you do see it once, I suppose that's possible, but then you're going to have a terrible estimator, because your estimator is just going to keep changing as you keep simulating for the rest of your life and don't see it again. So the trick is to use a coin, instead of using a fair coin for your flips, use a coin that's weighted to get heads 85% of the time. Because then on average, you'll go to the right 85, you'll go to the left 15, and you'll end up on 70. You have to correct for this fact that you used a biased coin with a likelihood ratio, but you can do that in your Monte Carlo, and you can find this probability to a lot of precision. You can get bounds on the precision. The issue is if you choose the wrong bias coin, so now if I'm biasing 95% to get heads and 5% to get tails, I get a really bad estimator, right? And you might think that, well, but my indicator function turned on, right? Things look good. I'm completely missing the sort of mass of this density, which is right here with this estimator. So if we were thinking about, so this is 2 things. So if you were sampling here, it's not like you could reweight your samples from my initial sample and somehow magically get samples there, right? So you can't do that. The other issue is this sort of idea of the threshold. Well, it's going to be quite different depending where I am in the valley, right? So obviously, if I'm closer, a much smaller volume flow will get to me than if I'm far down valley, right? So really, what we have here in this problem are many local problems, right? We have many local optimization problems to think about. What is this threshold effectively for each location? Okay, so right, so this is a workshop on surrogates. So we're going to use Gaussian processes, a sort of standard thing that we saw in the last couple of days. And so can we emulate the whole map at once? And I say no. And there's a couple of reasons. So we have multivariate output that's topographically dependent and has these sort of complicated spatial footprints. And then many scenarios lead to no flow at many locations, right? So we have a lot of zeros in our output. And then, so what our approach is to treat each map site individually and build M independent Gaussian processes in parallel. Okay, then we run a sort of wide design that would cover any of the locations of interest, any sort of important regions of input space, and we choose sort of site-specific sub-designs from the larger group of model runs. And here we need to include sort of important zeros that were close to the sort of more active set for a particular site. Okay, so we get this question a lot, and I should have said, when I had the collaborators, there are a lot of good students. There's a particularly good thesis by Ksenia Kirzarova this summer from Duke, a Jim and Robert's student, and this is really her work. So just think about what we could do. So I have a multivariate output, just 2 here in this example, and I build 2 Gaussian processes. So one way to think about the correlation here is just to take a linear model. And then you don't want to confuse this with the correlation we're thinking about for the Gaussian processes for the inputs, but here we can think about the correlation of the outputs here, of our multivariate outputs with this covariance matrix. I just want to look at 2 comparisons here that Ksenia did. So I have 2 functions, and basically just an exhaustive numerical experiment where I do a fine grid of kappa to go from being completely correlated, uncorrelated, anti-correlated, right? So, and here are just 2 of those functions there. And then I should say, performance-wise, if I look at these being independent, or if I try to put or if she tries to put a correlation structure on the output, they both perform very well, right? Both Gaussian processes perform basically the same and very well. If you do she did a sort of model selection on them. For different kappas, it might prefer, the model selection might prefer one or the other, and often it preferred neither. But I'm going to spare you those tables because they're not terribly interesting. But this is, I think this is these are the pictures that are more interesting. So here we have the sample correlation versus the correlation that we cooked up, right, by varying this kappa in this example. And there we have the estimated correlation from this linear model that we put on the output versus defined correlation. And for this example, looks great. If we go to another example and play the same game, right, so I'm going to vary kappa to go through these blue and green functions being completely correlated, uncorrelated, anti-correlated, and we look at the same pictures, right? So here we have, again, sort of, what the correlation should be for this output versus the sample correlation. Well, that's picking it up more or less, and we really have basically no predictive power from this linear model, right? So this isn't proof, but it's sort of a counterexample of imposing some structure on our outputs instead of using them independently. Okay, so back to Gaussian processes. So here we're going to run thousands of these at once, and right. So there's some things that we did for sort of sanity checks. First, we need sort of robust fitting. So there we looked, instead of at an MLE, at the mode posterior of a marginal maximum likelihood, and basically it just ends up being an easier optimization problem, effectively. And actually, Ming Yang has written up an R package called Robust GASP that will implement this for you. We needed a periodic correlation structure, and we came up with one. Which is fine. There's been a lot more work. I think people who are really focusing on that. So if you're interested in periodic correlation structures, there was a session or two on it in Lausanne. And then we need to sort of monitor that things are going okay. So we're doing this all in parallel, so we can have some extra overhead and do some leave one out experiments and just flag ones that seem like they're problematic on the leave one out experiments. The last thing I should mention, and I should have had a bullet point here, is that I'm feeding these Gaussian processes not to the height output, the maximum height of the flow, but instead to the log of that height plus 1. So this is problematic in some ways because the transformation does sort of bad things to the variance of the Gaussian process, but it's good in that it focuses on where the hazard is, right? So it sort of stretches out the small height events, which is what I want. And here it's transformed back, so you can't quite see that. But this is just the emulator at one site, right? So you can see here we have our maximum height, and the black dots are where the simulator was run. And we're looking, we have our angles here for our valleys and volume on a log scale. And then if we look at this from, so really what I'm looking at, I'm defining a sort of critical flow to be 1 meter. That's a bit arbitrary. It could be half a meter. Either is probably very bad if it's your house, right? So, but basically, I want to separate flows that lead to a meter of height from flows that don't, right? So here's looking at this same picture from the top, and effectively now I found this boundary, right, that I was looking for in my toy example, right? So if I'm beneath this curve, then I'm safe. If I'm above this curve, then I was inundated if I had run my computer model at one of the untested locations. Right, so now what this does for us is it makes this integral, and here we're going sort of back to the stationary case where it's Poisson and uniform and Pareto. Now this is a very cheap integral to evaluate, and I can throw as much Monte Carlo at this as I like. Right, so basically, am I on either side of this curve? Very cheap. Okay, so what I didn't tell you about at this point was there's some serious physical model inadequacy that we were dealing with. So the basal friction, which is part of what's slowing down these flows, is a material property, should be in the 25-degree ballpark, so up here. And it should be a constant. And here we're looking at sort of proxies from data of the basal friction, which is basically the get my tangent wrong, but the run out over the height drop. And we can see that we have this sort of effective basal frictions that are much lower for higher volume flows. And this is really bad if you want to do hazard forecasting, because the most dangerous flows are more mobile than the ones that you might be able to have data on and validate nicely. So this is a bad feature. So here we use some hierarchical modeling to take samples from this. There's enough data at Montserrat to sort of do the model directly. But I think in volcanology in general, this idea of pooling resources is super important, because if we wanted to do this at Semeru with these 4 data points that are clustered, we have crazy uncertainty bounds, right? But if we pool knowledge between the different volcanoes, those come down dramatically. Anyway, that's a bit of an aside. So here are samples from our model to fit this. And now I'm looking at volume on a linear scale in millions of cubic meters. Right, and really we were just doing this sort of hierarchical linear regression here to get these samples. Right, so here's what we do, and this is this is really sort of our strategy to overcome our model inadequacy, is to run our physical model at artificially low, artificial to the modeler's perspective, low basal frictions to get these more mobile flows that match up with what we actually see. Okay. So the design's funny here, but this is an old picture, so don't worry about it. But basically, here I have this basal friction volume space, and I have my samples from that space. So now I'm thinking about a three-dimensional emulator for inputs. And now I'm going to grab one of these samples and evaluate my emulator there. And then I'll get this sort of 2D surface like we saw earlier. Right, from that 2D surface, I can draw one of these contours that we saw, and we look on either side to see if we're inundated. And then I can repeat this process and get a whole family of these contours that are reflecting the uncertainty up here. Right, so now each of these corresponds to one of these samples of basal friction. And right, so we can demonstrate sort of some of the effects of epistemic uncertainty, at least in that model inadequacy issue on the problem. We can also just think about, instead of looking at the mean of the Gaussian process, of sampling the process directly. This is a more recent figure, so I've switched locations on you. But it's the same idea. So now I'm sampling the Gaussian process directly. So we have these sort of noisy contours. But we have including as much uncertainty as we can at this point. Okay, so here's our algorithm. So run a couple thousand Titan runs spread out over input space. For each location, then choose a sub-design, fit an emulator, do your sort of checks on that, evaluate the emulator at sampled basal friction curves, and draw these contours. Then you can choose your model for your aleatory variability, right? So, and then you run your probability calculations in parallel for all of these sites. So one is our expensive step. Two, we can parallelize. But the real key there is that this 4 is post-processing, right? Really 3 and 4 are post-processing, right? I don't have to have my model in hand, my scenario model to do this, right? You can give me a scenario model you like, and I can generate a map very quickly. Okay, so here's a sort of 2.5-year map using stationary assumptions at Montserrat. We can also think about epistemic uncertainty that's coming into those scenario models. So again, here's maybe the median fit of that Pareto. Here are samples of it. And each red curve corresponds to a different slope, right? A different alpha. But now my probability calculations are so cheap, I can compute a probability for each of these alphas, right? And then I can get a histogram of probabilities that, that reflects my uncertainty in my modeling in my input scenario. And do the same idea for the basal friction. I just want to compare these, right? So here, so in red, I fix the friction at the median and vary the alphas, and we can see the spread in probabilities. And for blue, I fixed alpha at the median and varied the friction. So we can see they're maybe kind of similar, but the friction's a little more important, or a little dominating the uncertainty a little more. But this is for a site that's quite up valley, right? So a relatively high probability of catastrophe. If we go to a down valley site, and we play the same game, effectively now we're completely swamped with this uncertainty in basal friction. Not knowing exactly what the slope of the tail was didn't really matter for this location. Basically, it takes a flow big enough that you would kind of be screwed anyway. Okay, so here looking at sort of retrospective validation. So again, using data here from 95 to 2003 to forecast forward for 5 or 6 years. And here I'm back in the stationary case, but I'm still thinking about, well, what if I was just sort of averaging over those two kinds of rates, or just at the low rate or just at the high rate, right? What would happen? And so these are what these maps look like. For the high rate, this one on the bottom, this is actually the within that period from 2004 to 2010, the map of the deposit of a flow that went down there, right? So it's plausible that what we're doing is reasonable, I suppose. Okay, so I want to think about what's next on this front. And really what we're interested in is cascading hazards. So this is Lassen volcano, which is in Northern California, sort of 2 or 3 hours from anything. But it's quite lovely. This is a little mountain lake right by it, but there's a town beneath Lassen called Chester, California, and that town has this reservoir, Lake Almanor. So what we're interested in, and here I'm sort of at the front end of the reservoir. It sort of goes back that way, and there's a dam at the back. Right. So we're interested in thinking about these sorts of pyroclastic flows that may hit. So the last time Lassen erupted was in 1915. It was relatively big flows, but they were headed basically in the other direction, away from the town of Chester. There are signs of activity at Lassen. So if you do various kinds of imaging underground, they're looking for hot spots. There are certainly signs of that at the moment. And so what we're thinking about is, what flows that would cause basically a wave that would take out the dam, right? That's what we're thinking about. And the approach we're going to take is really based on more of Ksenia's work from her thesis. So again, this credit should all go to Ksenia, but her approach was to come up with emulator composite functions, right? So here I'm thinking about the pyroclastic flow and then a wave model through the lake, right? So and her approach is to fit a Gaussian process to each function, and so here we've labeled those Gaussian processes G, M, and Fm, and then to look for this conditional density of the composition process, conditioned on knowing the Gaussian processes of each of the individual simulators, their hyperparameters, in particular the range parameters, and this is just at any input, right? So this, she's done all these calculations, and they're terribly messy, but they're actually not far from normal, which she proves. So she's taking normal approximations of this marginal density. And I know she's in the process of writing this up. I don't know if it's submitted, but these are from her talk at the last JUQ. So here we have two functions, just sort of toy functions to think about. So 3x plus cosine 5x, and cosine is 7z over 5 minus z. Right here are Gaussian processes fit to each of these. And what I want to compare is Ksenia's approach, which links the emulators, right? So we have these two emulators individually, we condition on them, and we get a linked emulator. So we have the true function in green, the mean of the Gaussian process in that kind of salmon color, and it works quite well. If you just emulate the composition itself, it does okay for this case. Right, so there is this region here in the input space that it misses a bit, but it's not terrible. But some other functions, it can be quite disastrous. So here we're looking at sine of 5x, and I do not think that's right, but another function, I'll fix it if slides are posted, but a cosine function. And here again is the sort of linked Gaussian process. It does just fine. Composing this introduces a lot more oscillation. And if you try to just emulate the composition of the functions, the emulator breaks down pretty severely. Right? So so certainly demonstrating that this sort of linked Gaussian process is a feasible approach and seems to work well is great. I also think in the, for doing UQ, it's a really nice approach as well, right? Because if we're, let me go back here, because now I can sort of play this game where I have uncertainty in my wave model, maybe uncertainty in the form of the forcing of that. But really, I can separate these problems, and I can think about what sort of impact forcing is going to create a wave that will break the dam, and then separate that into what sort of pyroclastic flow is going to generate that forcing. Right? And then play all the same kinds of games we've played with quantifying uncertainty along the way. So I think this is a promising approach. So I would be remiss to not plug next year's SAMC program, which is on model uncertainty, mathematical and statistical. I think that was a way to not say uncertainty quantification. For review purposes, I suppose. So this is next academic year. There's a kickoff meeting in August, and there's a summer school that Derek Bingham's going to host, I think along with Paul Constantine at Simon Fraser, which is just before, I don't remember the exact dates, but it's just before JSM, which is also in Vancouver this year. I don't think, so you can certainly look at some information is on the SAMC website for the kickoff meeting. For the summer school, I don't think there's information up yet, but it's happening as far as I know, so certainly keep your eyes posted. And then we have some tentative working groups here. So identify attacking model uncertainty, models across scales and disciplines. There's the other program that's going on is a personalized medicine, so there's going to be some interaction with that group. Some of the people that are, some of the organizers are quite interested in materials, so it'll be sort of a materialist informatics feel, stochastic discretization, quantifying uncertainty in extrapolative settings, and then just sort of foundation. So this is sort of things we're imagining will happen next year at SAMC, and throughout the course of the year, there'll be a series of workshops as well. So if you have any questions, you can talk to me or to Ralph. I'd be happy to try to help out. But SAMC is always happy to have people come in for, medium-term visits, right? So a week or more, or a semester. Those sorts of things are quite nice. And with that, I'll take questions. I'll also take answers if you have them.
So with these talks, I get a bit confused. So about the sort of data flow. So I like to use room. So in room 1, you fit an emulator, okay, with some data. Then in room 2, you take some of the inputs, and you just like the rest of the conference, you're using real data to tell you how to simulate the inputs.
Right.
And then you generate the outputs.
Right.
On the emulator. But then you also have data from the real world on inputs and outputs. So I get confused about. Are you calibrating the model, or are you varying the inputs? Are you calibrating and so on? Because you have this extra layer at the end which you.
Right. So there is no. So I'm not calibrating. So there's a big issue. For this particular model is that it's a live flow. So if I were to set my threshold lower, say to 5 or 10 centimeters, this flow would go forever and fill out the whole south of the island. And so there's stopping criteria, and it's a bit ad hoc, but we do not have data for live flows. Right, so when we started this, the validation sort of calibration problem was what we wanted to do, and the data doesn't exist.
So it's mostly just comparing the inputs to see what output
Right.
you get.
Yeah, that's really,
Error
yep,
bounds on the outputs. So
right.
very helpful.
So I have some two related questions, but so there is strong formal similarities with what we do in flood early warning systems, right? Indeed, the questions you have, maybe the energy slopes are different, but it's essentially the same thing. Now what you did is kind of co-creating, assuming that the off-diagonal structure is zero, and then of course you know it's not, because you show these color maps where you are interpolating between the different emulators, so you know it's not diagonal. And my question is, have you tried?
I'm not saying it's zero. I'm saying that we can't learn from it, which is a different thing.
And when you do croquet,
I mean, there certainly is correlation,
yeah,
right?
that's it, but the way you are doing your GPs, you are considering them independently. So basically, from a co-creating perspective, what you're saying is my covariance structure is diagonal.
On the output, so I just want to go to this. So on the left, this is treating them independently, the figure on the left, and then just calculating the sample correlation. They are correlated.
Yeah.
But modeling that correlation doesn't get us anything.
Yeah, because you try to learn these off-diagonal elements from data that is clearly not enough. And probably there is also a lot of uncertainty why you should put in these off-diagonal elements, the copulas, some people call it. So the question is, have you tried first to orthogonalize your outputs and then learn GPs on the coefficients of those orthogonalization, which is our approach, and we found it works much better than this.
So my intuition on this problem was, I mean, first wanting to have this independence in a computational perspective, right, which is going to make everything embarrassingly parallel, right, and simple that way. The other thing, imposing a correlation structure, I mean, it is correlated, I'm not arguing that. Imposing a correlation structure on something that that the spatial is so dependent on the spatial topography makes me nervous, because if I'm just thinking about cells going over from where I'm at, it's completely different if I'm in a valley than if I'm on a plain, right? So I think to sort of do that problem correctly is a quite hard modeling problem on its own, and not that you couldn't do it. But with this example, it says, well, maybe it's not going to get you anything anyway.
But I'm suggesting the opposite, that instead of throwing the correlation they exist and assume it's not there, what you could do is try to actually eliminate it from the data you're going to learn from. So this is in orthogonal decomposition, like snapshot. You have snapshots, and you're going to try to learn an emulator based on those snapshots, and you're doing it locally. So what you first try to do is that you actually get variables that are not your nodal values anymore, but are orthogonal in some sense, probably the orthogonality weighted by your differential operator you have there, and learn the GP on that. Basically what you're trying to do is to get actual Y values or actual outputs that at least try to have a diagonal covariance structure, and you learn GPs on those.
I mean, I guess in my perspective, I just don't think it's necessary for this problem.
And the other thing is you have this plot, you say, sorry, can I just, it's a couple.
Very quick, because there are other people who want to talk to you. Yes? No, you can ask your question.
So you say, when you try to learn the composite function, the emulator dies. You keep the same covariance structure, or you try to change it?
So no, it's the same covariance structure. It was fit to just the composite output, though.
So basically, it's an example of what we saw yesterday. Yes, you put the wrong assumptions, you get the bad emulator.
Right.
So it's not a proof of anything. What it means is you have to change your covariance structure to learn the composite output. Just that.
Yes, I would like to address that, though, but I think with her approach, what you can get away with is, and I don't disagree with you that it's cherry picked, right? That's not my point, but with her approach is that you can work with two simple emulators and get a good composite of them, right? That you don't need to do that step. Not that you couldn't do better than that. So you certainly could.
Another, yeah?
Just a simple question about, so you have a Poisson process and you have random walk and so. Is there any relation to the physics behind that? Like, are there people from seismics who could actually...
Yeah, so the physics, yes, so there's a lot of physics that's sort of hidden in that data, and a lot of it is from the dome forming structure of this volcano. So many flows are, so there's sort of this horseshoe at this particular volcano that if the dome forms at the base of the horseshoe, things are going to go to the east, especially if it's small. But sometimes the dome grows above it. If the dome grows above it, it can go any direction, and it can also take out part of the edifice. So it's so large events can change the morphology in a way that small events can't. Right, so that's, you know, that's I would say physically why you're seeing that kind of behavior, and the same thing with the rates, and it's kind of it's related to the extrusion rate, but it's a bit different in that when the dome is growing, it will slough off small events sometimes, but it doesn't do much, right? And when the dome is big and sort of ready to go, then the events occur more frequently.
If you take account of the seismic activity in the region, you could continuously improve your models.
Right. So I mean, that's something we're interested in, is how to effectively incorporate that precursor information. When we've looked at seismic data, we had a hard time seeing relationships between the seismic data and when events occurred. That doesn't mean, I mean, it might be that, you know, it doesn't mean it shouldn't be explored. And certainly I think any precursor information that you have is exactly the kind of thing we'd like to put into this.
How good are the forecasts for recent seismic events? So how are you validating? Are you validating?
Well, so what we're really, I mean, kind of stuck with are these retrospective validations. No, I'm way off here.
Assuming that you have access to recent data.
Right. So I mean, so here we can play this game where we hide the data from ourselves, right?
That's kind of cross-validation sort of thing.
Well, I mean, it is too, but honestly, my collaborator who made this picture pretty in GIS, she was shocked to see where the deposit hit, right? It wasn't, you know, this was what came out of just modeling the data up to 2004. So I certainly don't have any rigorous kind of validation on making forecasts.
I had a question about oh no, you have. Sorry.
I was just wondering how you did the grand design and then your sub-design.
So, the grand design is really just a Latin hypercube going beyond what the geologists would think is feasible to sort of cover the bases in volume in particular. For the sub-designs, basically looked for each location, looked for output that was positive, and then I think, how did we cut off? So there's a cutoff where we looked at the sort of how big of a flow going in the wrong direction would you need to get to the critical height. Right, so that was our volume range there. And generally for 2000, you'd end up with something on the order of 150 runs that would sort of be pertinent to one site.
So, how large is M in terms of the capital M in terms of the number of emulators?
So for this problem, it was also just under 2,000. For another problem I'm working on, it's more like 10,000.
Yeah. So, so Menyang's approach, I guess, the sort of parallel thing, and you said that you flag one if 1 in 20, so one's outside
Right.
95%, but Obviously, lots more can go wrong than that. I mean, you could, like, all of your emulators could just be all noise and swamping all of the...
Sure, sure.
10,000 emulators.
No, I mean, you don't. Right, so, so I mean, Mignon's approach is a bit different in... Mignon's approach is a bit different in that, right, we're sort of doing everything at once based on one set of range parameters. And here, each Gaussian process gets its own fit, so you're going to end up with smoother processes than Mignon would end up with.
So,
I mean, not that that's, you know, I mean, I think you're going to end up with less hassle in fitting.
I suppose I expected you don't because of the flag thing, but you flagged that thing up from nature at the start, the correspondence that says that people might forensically go over your uncertainty assessment. I guess, are you not worried about that?
No, I'm not worried about it in the sense that, I mean, I guess the other, the picture in some ways would tell you if something was very wrong, right? So the output picture, right? If there was a probability, you know, in that middle picture that was bright red at 1 pixel, right? That would be problematic. So I'm not overly concerned with the sort of interpolating tool and doing what we can there as being the base. I think there's probably bigger sources of uncertainty than that.
So I think we must close the session and thank our speakers.